Welcome to another amazing session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we enjoy solving the harder problems, but also we see the beauty and appreciate just the amazing intricacies in the simpler problems. So today we step back from the 2023 year of the MIT Integration B. We've exhausted the trigonometry related questions. We step back to 2022 and we go to the MIT Integration B finals in that year. We pick out problem number 2 because it's very interesting. And it's the integration of e to the power negative x times sine 3x over x, integrating from 0 to infinity. This is a very interesting problem. I hope you stick around and see how we're going to solve it. But before I jump into solving it, I'd like to appreciate our subscribers. Thank you so much for the support. And for those of you here who are here for the very first time, please give us that trust and tap on that subscribe button. For those of you who are coming back for the first, second, or third, or fourth time but haven't subscribed, please just give us that support. It means a lot because it will take us far. So let's begin solving this problem. So this problem is really painful because of that denominator, the x at the denominator. But we can take advantage of this concept known as differentiation under the integral sign. And what this essentially means is that if you're integrating a bivariate, and by bivariate I mean something that has two variables in it. So if we're integrating a bivariate function, f(x) and t, we're integrating from a to b, and if we take the derivative with respect to t of that integration, that's the same as integrating the partial derivative of that function with respect to t. So instead of integrating and then differentiating, you could as well just take the partial derivative of the bivariate function and then integrate the derivative of that function. So that's what it means. Now, this concept is popularly known as Richard Feynman's technique of integration. Why? Because he talks about it, and he talks about it being something that he used to solve very hard and complex integration problems. So we're going to use this technique. So what we're going to do is we're going to define another function, f(x) of t. Now our integrand is purely a one variable function. But if we introduce another variable, t, as shown here, such that when we derive dh, and when we derive ht as our integral with respect to t, we can take a partial derivative of the integrand, this bivariate integrand. So when we take the partial derivative of the integrand here, you see clearly the negative 2x comes out. And that x in the numerator cancels with what we have in the denominator. And we're left with the negative 2 right there. And so that eliminates the denominator that is a little bit convoluted. And we can integrate this derivative. So we can go further and express sine 3x using Euler's formula, which is e to the power I3x minus e to the power negative I3x over 2i. Now the 2's obviously would cancel, but also if you multiply both the denominator and the numerator with I, the denominator becomes -1. That cancels out with this negative next to the constant there. So essentially now we do have I integration from 0 to infinity of e 3i minus 2x minus e to the power negative into bracket 3i plus 2 of x. So very interesting. So we can easily integrate this problem. So integrating this exponential functions in as our integrand results in 1 over 3i minus 2t e to the power 3i minus 2t of x plus 1 over 3i plus 2t e to the power e to the power negative 3i plus 2t x, obviously from 0 to infinity. Now, this negative here disappeared because obviously when we took this constant down and it had a negative sign from the power here, the negative and negative multiplied becomes a positive. So substituting the limits, the upper limit as x tends to infinity of 1 over 3i minus 2t of e to the power 3i minus 2t of x minus limit x tending to 0 of 1 over 3i minus 2t e to the power 3i minus 2t of x. Now, as you can see, the 3i component, this complex, means that this is an oscillatory component, but the 2t is the extinction function. So essentially, as x goes to infinity, it dumps this oscillating function to 0. So this initial component tends to 0. And as x tends to 0, the entire numerator goes to 0. Any number to the power 0 is 1. So we're left with only the constant. And the same also applies to this second pair of terms. So we now have 0 minus 1 over 3i minus 2t plus 0 minus 1 over 3i plus 2t. So we can pull out the negatives, and so we have 1 over 3i minus 2t plus 1 over 3i plus 2t. So adding the fractions together, multiply the denominators, and then we have now 3i plus 2t plus 3i minus 2t. So the 2t's cancel out, and now we're left with, in the numerator, 6i over minus 9 minus 4t squared with a negative I as our constant there. So I times I is -1, and so the -1 cancels with that, but still we're left with the set of negatives from the denominator here, and so this results into -6 over 9 plus 4t squared. So dh dt is equals to -6 over 9 plus 4t squared. So what is ht? We'll just have to integrate whatever is on the right-hand side with respect to t. And we can use the substitution of t being equal to 3 over 2 tan theta, such that dt d theta is 3 over 2 sec squared theta, and so dt is 3 over 2 sec squared theta d theta. So now ht is equals to -6 over 9 plus 4 into bracket 9 over 4 tan squared theta times 3 over 2 sec squared theta d theta. This last term coming in place of dt. And so the 4 and 4 cancel, so we have 9 plus 9 tan squared theta in the denominator, and numerator still remains -6 times 3 over 2 sec squared theta d theta. So we can pull out the -6 and the 9 out, and so we're left with 1 over 1 plus tan squared theta times 3 over 2 sec squared theta d theta. The constant here is now -2 over 3 if we simplify 6 over 9. Now we can see that the 2 over 3 now would cancel out with the 3 over 2 to 1. And the sec squared theta in the denominator here cancels out with the sec squared theta in the numerator. And so we are left with the negative or minus the integral of d theta, which is the same as negative theta plus c. Now, since we say t is equals to 3 over 2 tan theta, then theta is the arctan of 2t over 3. And therefore, ht being equal to negative theta plus c is equal to negative arctangent of 2t over 3 plus a constant c. Now, to solve for c, that constant, if t tends to infinity, the ht in the original equation, the bivariate equation that we formula or function or the integrand that we created, as t tends to infinity, this exponential term tends to 0, and so the integral, the entire integral, tends to 0. Therefore, the limit of t tending to infinity of the negative arctangent 2t over 3 plus c, this negative arctangent 2t plus 3, if t tends to infinity, means this entire component tends to negative pi over 2, and then c remains there. But we know that the entire integral is 0, so 0 is equal to negative pi over 2 plus c, and therefore c is pi over 2. That means that our ht is the negative arctangent 2t over 3 plus pi over 2. But our question was the integral of negative 2tx sine 3x over x from 0 to infinity, which means that it's the same as t being equal, or h with t being equal to 1. So which is the same as, so h1 is equal to negative arctangent of 2 over 3 plus pi over 2. So this is the answer of the integral. But, you know, it is not very simple. We could simplify it further by taking the tangent of the h of 1, which is a tangent of the negative of arctangent 2 over 3 plus pi over 2. And so using the difference formula for tangent, which is the same as tangent of pi over 2 minus tangent of the arctangent of 2 over 3 plus 1 plus, over 1 plus tangent of pi over 2, tangent of arctangent of 2 over 3. Now divide through by the numerator and denominator by tangent of pi over 2. That results into 1 minus tangent of the arctangent of 2 over 3 over tan pi over 2, 1 over tan pi over 2 plus tangent of arctangent of 2 over 3. Now, tangent of pi over 2 means as we approach there, this entire value approaches infinity. So whatever has tangent pi over 2 in the denominator tends to 0. So we're left with 1 over tangent of the arctangent 2 over 3, which is 1 over 2 over 3, which is just a reciprocal of 2 over 3, which is 3 over 2. Therefore, tangent of h1 is 3 over 2. That means that h1 is the arctangent of 3 over 2. And so the other expression for the answer of the integration of e to the power 2x sine 3x over x from 0 to infinity is same as the arctangent of 3 over 2. So this is the answer for this question. And it involved using quad and quad, the Richard Feynman technique for integration. But the real name, the technical name is using the technique of differentiation under the integral sign. And this can really help you solve very intricate problems that have x in the denominator. For example, the integral of sine x over x. You could introduce or create a bivariate function with another extra variable such as t to be able to solve it. And then obviously the manipulation at the end where you try to now solve for the constant c, that's also important. So thank you so much for hanging out with us. It's been a real pleasure hanging out with you. Thank you so much. It's been a blessing. Until next time, please, for those of you who have not subscribed to our channel, please subscribe to our channel. We really need your support and we really appreciate it. Thank you. Till next time. Bye-bye.